In this video, we're going to look at the graph of f of x and its inverse. We're going to look at restricting the domain of a function to ensure it has an inverse. We're going to look at the horizontal line test and also domain and range properties of the inverse function. We're going to start with the problem where we find the inverse of f of x equals x cubed plus 1, graph f of x and its inverse, and then show solution points for both of these functions in our graph. We start by finding the inverse function. And we use the procedure where we replace f of x with y. We switch x with y to get the equation x equals y cubed plus 1. Then we solve that for y, subtract 1 from both sides, then take the cube root of both sides. We get y equal the cube root of x minus 1. That's our inverse function. Now we're going to graph both f of x and this inverse function on the same graph. Now I'll go through the points of f of x and then we'll see the pattern that shows up for the inverse function. If we plug in -1 into f of x, we get 0 for y. If we plug in 0 for x in f of x, we get 1 for y. If we plug in a half, we get a half cubed, which is 1/8, added to 1 makes 9/8. And when we plug in 2 into f of x, we get 9. And here's all the points plotted for f of x. We get this S-shaped curve. Now let's look at the graph of the inverse function. When x is 0, we get y equal -1. When x is 1, we get y equals 0. When x is 9/8, 9/8 minus 1 is 1/8. And the cube root of 1/8 is 1/2. And also when we plug in x equal 9, we get 2. And if you notice something here, all the points of f of x are showing up in the inverse function except x and y have just been switched with each other. Well, that makes sense because how do you find the inverse? You just switch x with y and just rearrange the equation that you have. You don't change the equation. All you do is really switch x with y. And if you look at the graphs of these two functions, we have f of x is this S-shaped curve that goes up, but then the inverse function has the same shape except it's a mirror image across the line y equal x. And that's because all we've done is switched x with y and rearranged the equation. So two things you're always going to see happening with the function and its inverse. The graphs are going to be mirror images across the line y equal x. And also the solution points for the inverse may be obtained just by reversing or switching x with y in the f of x solution points. Okay, now let's look at the problem where f of x is x squared and we want to find the inverse function. Well, if we follow that procedure, we replace f of x with y, we switch x with y, and we get x equal y squared. Now we solve for y by square rooting both sides. So you get y equal plus or minus the square root of x, and one might conclude that f minus 1 of x, or the inverse function, is plus or minus the square root of x. But there's a problem here. If we plug -3 into f of x, we get 9. If we plug 9 into our inverse equation we have here, we don't just get -3, we get plus or minus 3. It's not even a function. In fact, if we graph both y equal x squared and this y equal plus or minus the square root of x, we see that plus or minus the square root of x is a sideways parabola. It's not a function. It fails the vertical line test. So here we say that for the domain of all real numbers, f of x equal x squared does not have an inverse function. But can we restrict the domain so f of x will have an inverse? The answer to that is yes. If we restrict the domain to x greater than or equal to 0, when we take the square root, like we did above here, of y squared, we don't get a plus or minus. We get f minus 1 of x is just the square root of x. And I show what the effect of restricting the domain in this graph here. I've taken away the left side of this parabola because we no longer have negative x values. So we just have the parabola going up on the right side. When we do the inverse, we only get the top half of the sideways parabola, and it is a function. It passes the vertical line test. And this leads up to something called the horizontal line test. If a horizontal line passes through two or more points of the graph of f of x, then f of x will not have an inverse function for that given domain. And here are two examples. The first example is y equal x cubed over 5. This will have an inverse function no matter what horizontal line you pick. It only passes through one point. But we look at the example on the right, y equal x squared plus 1. There are many horizontal lines that pass through 2 or more points. So y equal x squared plus 1 does not have an inverse function for its given domain of all real numbers. So can we restrict the domain of f of x equal x squared plus 1 so that it will have an inverse function? And the answer to that is yes, you can. And we're going to do that on the next page. Okay, we're going to restrict the domain of f of x equal x squared plus 1 so that it has an inverse function. Then we're going to graph both f of x and its inverse and state the domain and range of both f of x and its inverse. We start by restricting the domain. Since x squared plus 1 does not pass the horizontal line test, we have to take away part of that domain so that it does. Well, the easy choice here is just to let x be greater than or equal to 0, and I have this shown on the right. The graph on the right does pass the horizontal line test. Now we can find the inverse. So we write this as y equal x squared plus 1. We switch x with y, then we subtract 1 from both sides and get x minus 1 equal y squared. We extract square roots and we get f inverse of x, or f minus 1 of x, is the square root of x minus 1. There's no plus or minus here because the y values were restricted to positive values only since y was formerly x. Now we graph both of these. For f of x equal x squared plus 1, we have the point 0, 1 and 1, 2. It's the right side of a parabola shifted up 1. For the inverse function, we can just reverse those points and plot 1, 0 and 2, 1, and note that it's going to be a mirror image across this 45-degree angle line y equal x, and we get the top half of the sideways parabola. Now we have to find the domain and range. Well, we can find these from the graph. For f of x, we restricted our domain to x greater than or equal to 0, so that's our domain. From the graph, we see that the graph starts at 1 and goes up to infinity, so f of x has a range of 1 to infinity. Now for the inverse, the domain of the inverse starts at 1. The x values of the inverse graph start at 1 and go off to infinity. The y values, which would be the range, start at 0 and go to positive infinity. And you notice something here. The domain of f of x is equal to the range of the inverse. And the range of the f of x function is equal to the domain of the inverse. And I have a note here that in general the domain of f of x will equal the range of its inverse, and the range of f of x will equal the domain of its inverse. That will always be true, and it's true because the inverse is obtained just by switching x with y.